Okay, I'm going to talk about the basis section in the textbook. First, I want to introduce this problem, this quiz problem, and you should think about these answers and come up with your own idea. And you may be asked this on a quiz or a test. All right, so, if you want to answer these questions, you should visualize a specific situation. Just to choose some set of vectors and see what you can do with them. All right, so part A says, if the set of vectors u is linearly dependent, then there exists a set of vectors v that contains u and is linearly independent. All right, think about what linear dependence means, and can you find a larger set that contains a linearly dependent set that is linearly independent? So think about what that means. All right, so B, if a set of vectors u is linearly independent, then there exists a set of vectors v such that v is contained in u and v is linearly dependent. So in other words, if I have a linearly independent set, can I find a smaller set that is linearly dependent? Because v is contained in u. So think about what this means. In this case, v contains u, so u is the smaller one, and v is the bigger one. And here we're saying that u is linear dependent and v is linearly independent. So the question is that possible? For part B, let's just do a different color here. For part B, what it's asking is u is bigger than v, so u is bigger than v, and v is smaller. Right? So in this case, u is linearly independent and v is linearly dependent. So the question is that possible? Think of some examples and come to your conclusion. Part C says, if a set of vectors u is linearly independent, there exists a set of vectors v that contains u and is linearly dependent. So this one I could draw as u is the smaller set, v is the bigger set, and in this case u is linearly independent and v is linearly dependent. Okay. Then D, last one, is saying here, let's see, v is contained in u, so v is the smaller set, u is the bigger set, and here we're saying that u is linearly dependent and v is linearly independent. So the question is, which of these scenarios are possible? And the answer is either true or false. All right, so that's a good thing to think about. All right, let me go on and pick up on something that was introduced in the LISS section, but it's going to be used very heavily in the basis chapter. Suppose V is a vector space and B is a linearly independent set that spans V. Let W be any vector in V. Then there exists a unique set of scalars A1 through AM such that V equals A1, V1 plus AN, VN. So W is a unique, the unique linear combination of linear independent vectors. Okay. And you can read in the book why that's true. Basically, if there were two different linear combinations, then you could show that the V's were linearly dependent. But if you've got linear independence, you have unique linear combinations. So if the V's are linearly dependent, then the expression of W as a linear combination of V's is not unique. Okay? So what linear independence gives you is this uniqueness. There's only one way to express the vector W in terms of linear combination. All right? So that brings us to the idea basis. All right, so the subset S is subset of V is a basis of V if it's a linearly independent set and spans V. So let's think of some examples. Just get a very simple example. Let's look at P1. That's polynomials. So that's equal to the set A plus BX, where A and B are, well, I'll use our complex numbers or real numbers if you want to do real vector space. Now, if you look at this, you can write this as A times 1 plus B times X. Okay, so that means that P1 is equal to the span of 1 and X. All right, now are 1 and X linearly independent? Yes. Why are they linearly independent? Because A times 1 plus B times X equals 0. That's a linear dependence relation. Is only true if A equals B equals 0. All right. So here's an example of a basis. 1x is a basis for P1. This should be P1 of x. Sorry, let's do it that way. All right. So then there are many, many other examples of bases. In fact, in the next slide, we have another example. The columns of the identity matrix IM form a basis for the vector space CM. Let's blow this up a little bit so you can see it. All right. So why is that true? Let's look at the example again. Let's look at I3. And that's 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. These form a basis for the vector space CM. Why? Because if I have x, y, z, which is an arbitrary element of C3, I can write that as x times the first column plus y times the second column plus z times the third column. All right. And certainly these three vectors are linearly independent. So the vectors are linearly independent. All right. The only way to get 0, 0, 0, y equals 0, z equals 0, is the only possible way to make that happen is to make x equals 0, y equals 0, z equals 0. So let's go on and do some practice. For instance, how would you find the basis for the column space of this matrix? Now, we just employ techniques and solve problems that we've done before. What we want is we want a linearly independent set, that has the same span that spans C of A. All right. Now there are two ways to do this. One way is to row reduce and identify the pivot columns. That's going to give me a linearly independent set of columns that has the same span as the three columns. Another way is to transpose and notice that the column space of A, I'm calling this A, column space of A is the row space of A transpose. And the row space doesn't change under row operations. Okay, so let me do it that way. If I do the transpose, you can see the transpose down here. Let's just verify that that's true. Okay, here I had 1, 2, minus 1. Now it's going down the column. Here I had 3, 1, 0, second row. Now it's the second column. 4, 2, 0, third row is the third column. Now I do some row operations. I reduce, 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 and I get to this place here. Now, you could continue to row reduce. However, I can tell that these three vectors, these three row vectors, are linearly independent. How can I tell that? Well, if you try to form a linear combination of these three rows, which I've done here below, and you try to find A, B, and C, that gives me 0, 0, 0, look at the first component. The first component is minus A. And that gives me A is equal to 0. Second component gives me 3B equals 0. So b equals 0. Now, if a equals 0 and b equals 0, then the last component gives me 0 times 0 plus 0 times 4 plus c times 2/3 equals 0. That gives me c equals 0. So the point I want to make is you don't need to row reduce all the way. Just row reduce to the point where you can tell the vectors are linearly independent. And these are linearly independent because if you try to form a linear combination, you can read off of the linear combination that each of the coefficients would have to be 0. All right, so that's a good practice. Let's do another problem. These are exercises for practice. I recommend that you do these. These are in the basis chapter. So please practice on these. And let me look at one here. Here's one from the chapter. Let T be a subspace of P3 such that T is equal to the polynomials of this form, a plus bx plus cx squared plus dx cubed, such that the second derivative of P is equal to 0. Second derivative of P at 0 is equal to 0. Second derivative of P at 0 is equal to 0. Find a basis for T. All right, so we're kind of mixing algebra and calculus here. We're looking at any polynomial. I think that's actually C13. We're looking at any polynomial in P3, and we're looking only for those polynomials whose second derivative at 0 is equal to 0. All right, so now, how would we do this? Well, let's see what this condition implies for the coefficients a, b, c, d. What does this tell me about the coefficients? Well, if you take the second derivative, you can take the second derivative term by term. Second derivative of a is 0, second derivative of b is 0. Second derivative of cx squared is 2c. Second derivative of dx cubed is 6dx. All right. Now, if I look at p second derivative of 0 equals 0, that gives me that 2c plus 6dx is equal to 0. And this is at x equals 0, so that tells me 2c equals 0. Okay. So in fact, the polynomials in T all have the form a plus bx. Now I have to take out the 0x squared term because c has to be 0 plus dx cubed. Now this is an arbitrary linear combination of 1x cubed, so 1x cubed is a basis for T. All right, so that's how you do it. You look at your subspace, characterize it in terms of linear combination, make sure that the vectors in the linear combination are linearly independent, and then you've got a basis. One more problem on this section. All right. So here we have a subspace of P3 such that T is the polynomials a plus bx plus cx squared plus dx cubed such that P of 7 equals 0, P of minus 3 equals 0. Find a basis for T. Now I recommend that you stop the video and try to do this yourself. Remember what I said in the previous problem. See what these two conditions say about A, B, C, and D. Then try to characterize the resulting set using these conditions, and then try to write as a linear combination. All right, so I suggest you stop the video and see if you can do this. All right, so let's go ahead and do the problem. The two conditions, P of 7 equals 0, P of minus 3 equals 0, can be expressed by plugging 7 in for x to get one condition, and plugging minus 3 in for x to get the second condition. So P of 7 equals 0 implies a plus b times 7 plus c times 49 plus d times 343 is equal to 0. Right? That's the expression for P of 7. P of minus 3 equals 0 means I can plug minus 3 in for x, and I get a plus minus 3b plus 9c plus minus 27d. And that gives me 0. All right, so these are the conditions on A, B, C, D that result from the two conditions that were given to me. Now I can write this as a set of linear equations involving A, B, C, and D. And in fact, what I'm finding is the null space for a given matrix, okay, by a null space of a 2 by 4 matrix, a problem I've already solved. So let's go down and row reduce. And once you row reduce, you get this system. And that gives me equations for A and B in terms of C and D. C and D are my free variables, A and D are my pivot variables. I can write this equation in vector form as follows: a, b, c, d equals, and so on. You can see how these equations follow from the form here. So I can write a, b, c, d in terms of free variables as a linear combination of free variables. So since this is true, I can write a plus bx plus cx squared plus dx cubed as c times a polynomial, which is represented by this vector, plus d times another polynomial, which is represented by the second vector. So I have two basis vectors, minus 21 minus 4x plus x squared, minus 84 minus 37x plus x cubed. All right, now that's the hard way. There is an easy way, which is kind of clever. Now, if p of 7 is equal to 0, remember what p is. P is a polynomial of degree 3. If p of 7 equals 0, you know from your algebra class that x minus 7 must divide p of x. So that's something you learned from high school algebra, that if you have a root of a polynomial, then x minus that root divides the polynomial. Then you can do long division and factor the polynomial. All right, now we similarly have p of minus 3 equals 0. Same reasoning. And that tells me that x plus 3 divides p of x. All right, so in fact, x minus 7 times x plus 3 must divide p of x. Since p of x has degree 3, then the only thing that can be left over is a linear term. So p of x must be some linear polynomial times x minus 7 times x plus 3. Right. So I can write that as a times x times this plus b times this polynomial. That's a linear combination. These two are also evidently linearly independent because the only way to make this combination 0 is to make a equal 0 because of the x cubed term, and to make b equal 0 if a equals 0. So this is a different basis. Okay. Now notice a single subspace can have many different bases. You don't just have one basis for a subspace. So now that you've watched this video, I recommend that you go to the basis section of the course outline, work through the problems listed under competencies, which have answers, and do enough of the exercises, practice exercises without solutions, to make sure that you're comfortable with doing this. All right, so that's it.